Hey, welcome. Today, we are diving deep into something that secretly runs the world around us. It's called graph theory. And believe me, it is the key to understanding just about everything, from your friends list to the entire internet. So let's peel back the curtain and see how it all works.
So, let me ask you a question. What could your circle of friends, the World Wide Web, and a basic roadmap possibly have in common? I mean, on the surface, they seem like they're from completely different universes, right? But what if I told you there's a single, fundamental idea that connects them all?
Well, it turns out that's exactly it. They're all just networks. They're all about points connected by lines. And in the world of mathematics, a network of connections has a special name: a graph. It's a ridiculously simple idea, but its power to model and solve problems is, well, it's just incredible.
Okay, so let's start with this big picture idea. What does it actually mean to see the world as one giant graph?
At its core, a graph is made of just two things. You've got vertices, you can just think of those as the dots, and you have edges, which are the lines connecting the dots. That's literally it. The dots or vertices are the things in your network, and the edges are the relationships between those things.
And this is where it gets really cool. Think about it. In a computer network, the vertices could be cities, and the edges are the data cables running between them. Or in a social network, the vertices are people, and the edges are their friendships. See? You can pretty much model anything you want this way.
But, not all connections are the same. The way those edges work, the rules of the road, so to speak, can change absolutely everything. Let's look at one of the most important differences.
So, we basically have two main flavors. First, you have an undirected graph. Think of this like a two-way street. The connection is mutual. If Sheila is friends with Feroz, then Feroz has to be friends with Sheila. It goes both ways. But then you have a directed graph. This is a one-way street. Think about following someone online. You can follow them, but that doesn't mean they automatically follow you back. The connection only points in one direction. This is all great as an idea, but how do we actually get a computer to understand this? How do we translate this picture of dots and lines into something a machine can actually work with? Well, there are a couple of really smart ways to do it. The first approach is called an adjacency matrix. And you can see it's basically a giant grid, like a spreadsheet. You list all your vertices down the side and across the top. If there's a line connecting two of them, you put a 1 in the box. If not, you put a 0. It's super straightforward, but if you have a huge network with only a few connections, you end up with this massive table that's almost entirely full of zeros. Kind of wasteful. Luckily, there's a much cleaner way, the adjacency list. Instead of that giant, sparse grid, each vertex just keeps a little list of its direct neighbors. That's it. Vertex A is connected to B and D. Vertex B is connected to A and C. There's no wasted space, no storing a million zeros. It's way more efficient.
All right, so we've got our graph, and we've stored it in the computer. Now, how do we actually get around in it? Turns out there are some important rules for how you navigate these networks.
First, we need to get a couple of terms straight, the difference between a path and a walk. A path is like a very strict trip where you are only allowed to visit each dot, each vertex, one time. No going back. A walk is a lot more casual. You can wander around and revisit vertices as many times as you like. It seems like a tiny difference, but for a lot of the algorithms we use, it's an absolutely crucial distinction. And that idea of getting from one place to another leads us to a really key property of a graph, whether or not it's connected. A connected graph is simply one where you can get from any vertex to any other vertex. There are no isolated islands, no little groups of dots that you just can't get to from the mainland. Okay, now we get to the really fun stuff. We have the building blocks, we have the rules, so let's see how we can use graphs to solve some seriously interesting real-world puzzles.
First up, we have something called breadth first search, or BFS. The best way to think about this is to imagine dropping a pebble into a calm pond. The ripples spread out, right? One layer at a time. BFS does the exact same thing. You start at one vertex, visit all of its immediate neighbors, then you visit all of their neighbors, and so on, spreading out layer by layer. And the coolest part? This strategy is guaranteed to find you the absolute shortest path between 2 points.
Now, the other big strategy is called depth first search, or DFS, and this one's completely different. DFS is like trying to solve a maze with your hand on the wall. You pick one path and you just go as deep as you possibly can. When you finally hit a dead end, you backtrack just enough to find the next path you haven't tried yet and you dive down that one. DFS is perfect when you need to explore every single nook and cranny of a graph.
Now take a look at this number. Just 4. It doesn't look like much, does it? But I'm telling you, in the world of graph theory, this number is an absolute legend. So what's the big deal with 4?
Well, it's because of one of the most famous and mind-bending results in all of mathematics, the four-color theorem. It says that you can take any map you can possibly imagine, no matter how ridiculously complicated it is, and color it in with just 4 colors, without any two bordering regions ever sharing the same color. It's a simple idea with a proof so complex it required a computer to solve, and it's all powered by graph theory.
Okay, let's look at one final and super practical application, using graphs to figure out the right order to do things.
This is a process called a topological sort. It sounds fancy, but all it is a way to line up all the vertices in a directed graph into a single straight line. And the one rule is, for every connection that points from vertex U to vertex V, U has to come before V in that line. But simply, it's about creating the perfect to-do list where you respect all the dependencies.
But, and this is a big but, there is one critical rule. This only works if your graph doesn't have any cycles. It has to be what's called a directed acyclic graph, or a DAG. I mean, it makes perfect sense, right? You can't make a sensible to-do list if task A depends on finishing task B, but task B depends on finishing task A. You'd be stuck in an infinite loop forever.
So why should you care about this? Well, you use it constantly, every single day. It's how your computer figures out the right order to install a piece of software and all of its required packages. It's how a university makes sure you've taken the intro class before you sign up for the advanced one. It's the hidden logic behind every good project plan. It is, quite literally, everywhere. So there you have it. From your social life to coloring maps to just getting things done in the right order. Graph theory gives us this amazing new lens to see the hidden connections that shape our world. The only question left is, now that you have this tool, what connections are you going to start seeing? And what problems are you going to solve?